finish up looking at section 5.4. So the very last thing we didn't get to yesterday in part 1 was properties we can use to either take two logarithms that have an argument that's combined and separated, or take two logarithms that have already been separated and combine them into one. Okay, so those are the properties that we're going to take a look at. So the first property deals with a product inside the argument. So this applies for any base. Okay, the base has to be the same. Whatever base you start with, that's going to be the base that you finish with. Okay, the base does not change. So this says that log base A of m times n equals log base A of m plus log base A of n. And here's an example with numbers. And we could try that one. So I'll type it in just so you can see how it works. And I'm going to use common log because I have a button for that. So I'm going to take the log of 20, and I get that as an answer. And then I'm going to take the log of 4 plus the log of 5. Okay. It comes out exactly the same. What's another way that you think I could get the same answer instead of putting a 4 and a 5 here? Yeah?
You could do a 2.
Yeah, any two numbers that multiply to give you 20. When you put them in the formula, if you put it in as a sum, it will give you that 1.3. Right? You could do 40, and you could also do 1/2, because 40 times a half is also 20. Okay, so that's the formula. When you have a product, it turns into a sum. How about when you have a quotient? What do you think a quotient inside the argument would turn into? Yeah?
Subtraction.
Yep, that would turn into subtraction. What's important here is when you do the subtraction, order matters. You have to make sure it's the log of the numerator minus the log of the denominator. Question on that one. It's the second property. And the third property. Let's look at something like this. Log of x cubed. Base 10, common log. What's the long way to write out x cubed? Instead of using an exponent. Yep.
Like x times x times x.
Right. That means log of x times x times x. Now, this property that we did, property 1, I had a product of two things inside the parenthesis. It would apply to a product of as many factors as you have. You can always split all your multiplication into separate additions. So we had two factors. It split into two things when we did the sum. I want to split this one up. When I split it up into addition, how many things do you think I'm going to be adding together? Yeah?
3.
3. Can you tell me what the 3 things would be? Using that first property?
Would it just be log x plus log x plus log x?
Yeah, it would be log x plus log x plus log x. Now, log x plus log x plus log x, we could combine that and write it in a shorter way. What's log x plus log x plus log x? Yeah?
3 log.
3 log x. So what happened to get from here to here? So we don't have to go through all those steps in the middle. Does anybody notice? Yeah?
We just took the 3 from the
Right, the exponent on the argument went in front. Right, so that's property 3. Anytime you have an exponent on an argument, you can take the exponent and put it in the front of the log, just like that. Okay, what that is doing is it's called writing a power as a factor. So when you see directions that say something like express powers as factors, that means to do rule 3. Don't leave things as powers. Put them in front as multiplication and make it a factor, like that. Now, sometimes you might see something like this. The log of the square root of x. And if you wrote that as a final answer, and I said, don't leave any powers in the problem, this is wrong. You've left a power in this problem. It's hidden, but you did leave it. What power have we really left on the exponent of x there? Yeah? We've left an x to the 1/2. So what you should do, if you have a square root, and it says specifically, do not leave powers in the final answer, you should change the x to a x to the 1/2, and then the 1/2 should go in front. That's how you write this without any powers. Any questions on that? And I think I wrote that. Yeah, that's what I just wrote right there. So remember, for cube roots, it's a 1/3 power. Fourth root's 1/4 power. Any root. Okay, we always want to make sure, if the directions say to get rid of the power, put it in front. All right, so now we'll try first taking things that are already combined together and splitting them apart into multiple logs. So this one says, separate into multiple logs. If you are left with any powers, write them as factors. Don't leave them in the exponent. Okay, so we only have 2 rules for what's happening inside the argument. Either you have 2 things multiplied, or you have 2 things that are being divided. And that controls whether it's a sum or a difference when you split it. How is this log going to split into 2? Will it split as a sum or as a difference? Yep. Yep, it's going to be a sum. I'm going to have 2 logs. What's going to be the base on each of my logs? Yep, 4. The base has to stay the same. 4 and 4. What's going to be the argument to my first log? Yep, 3. And the argument to my second log? X. Good. And that's it. That's how you would take what I've given you in example A and split it into 2 logs. Any questions on that? So there were no exponents in them. Let's look at B. Log base 2 of 5r cubed. Okay. How is this one going to split? Will it be a sum or a difference? Yep. Sum. Right? Overall, it's just something times something. So we'll have a sum of 2 logs. Okay, base on each log will be? Yeah, 2. Base has to stay the same. And what's going to be the argument to my first log? Yeah, it's going to be a 5. And how are we going to write the second log, making sure we follow the directions, express powers as factors? Yep. 3 log base 2 of r. Yep. So you could start out with log base 2 of r cubed, but then the cube has to go, or the 3 has to go in front. Just in front of its log, not in front of the whole problem. Okay. Just like that. All right, let's try this one. Anybody think they could just split that and give me the whole thing and the final answer? Yep.
Log base 9 of x minus log base 9 of z.
Yeah. So it's log base 9 of the numerator. This time it's minus because we have division. Log base 9 of the denominator. So we did it with base 4, base 2, we did base 9. What base are we doing in this one? Yeah?
E.
Great, we're doing it with base E. We don't have to write base E. We're going to use the abbreviation, like we always do. So when we split this one up, you're not going to write LOG, you're going to write LN. So that's going to keep the base the same. All right, anyone think they can give me the final answer for that one? Yep.
3 ln of y minus ln of e.
Yep. So if you did it in a couple steps, you might do ln of y cubed minus ln e, but then because there's a power, you have to put the power in front because that's part of the directions of these problems. If it's not in the directions, then don't worry about putting the power in front. All right, let's try this one. So ln of x squared divided by x minus 1 cubed. Okay, so first thing, is this going to split as a sum or a difference? Yep.
Difference.
Yeah, overall it's a difference. You've got something in the top, and then you've got something else in the bottom. Okay, so let's do ln. ln, it's going to be a difference. The first ln is going to be what? Yep.
2 ln x.
2 ln x. Yep. And the second ln? Yep.
3 ln of x minus 1.
Yep, and you do need to keep that x minus 1 in parentheses, especially when we start to talk about transformations, because there's a difference between this and that. The top one is a horizontal shift 1 unit to the right. The bottom one is a vertical shift down 1. Okay, so if you want that minus 1 to be part of what it originally was, if the x minus 1 was all together, you got to put parentheses around the argument. Same thing when you graph it on the calculator. If you don't put parentheses around the x minus 1, once the calculator hits an addition or subtraction sign, that's where it stops thinking things are part of your ln. Okay? So that would not think the minus 1 should be part of the ln in the bottom. Okay, any question on that? All right, let's try this one. So this time it's log base a. The numerator is the square root of x squared plus 1. And the denominator is x cubed times x plus 1 to the 4th. How many logs do you think this is going to split into? Have a guess? Yep.
3.
Yep, it's going to split into 3. And kind of the order of operations is if there's a difference of logs you have to deal with, do that first. And then if if you have a product of logs, either in the numerator or denominator, do that second. So let's start with the difference. We're going to have log base A, and let's deal with just the numerator. How are we going to rewrite the first log so it doesn't have the square root anymore? Yeah.
You put the 1/2 in front.
Yep. I'm going to put a 1/2 in front. And what are you going to put after the log?
X squared plus 1.
And how are you going to write it?
In
In parentheses. Okay, that pretty much takes care of the top. There is nothing else to do there. That's as simple as you can make the top. Now, in the bottom, we've got a fraction. So we're going to do divided by. And now the bottom is like its own separate problem. We have, we'll do it in 2 steps. Log base A, x cubed times x plus 1 to the 4th. Okay, and just to be clear, all of that is part of my log. Now we've got to split that second one up. How's the second one going to split? As a sum or a difference? Yeah, that's going to split as a sum. We still have this minus in front, but what's inside is going to split into a sum. What's going to be the base on each log that it splits into? Yep, base A. And what's going to be the final answer for the first log inside the brackets? Yep.
3 log x.
Yep, it's going to be 3 log x. And how about for the second log inside the brackets? Yep.
4 log x plus 1.
And
X plus 1 is in parentheses.
x plus 1 is in parentheses. Yeah. So you can leave your answer like that. If they asked you to distribute the negative, you could write it as 1/2 log base A x squared plus 1 minus 3 log base A x minus 4 log base A x plus 1. So that'd be the only other thing you could do is distribute that negative. But that's fine. All right, so that's taking a single log, and splitting it into multiple. Now we're going to do the reverse. We're going to take multiple logs and combine them back together. So it says to combine them into a single log and express factors as powers. This means don't leave any numbers in front, put them back as exponents. So now do everything we just did in the previous problems, but in reverse. So what do you think the first thing we would do here to get this ready to start combining back together? Yeah.
Write the base along the find the common.
Okay, so yeah, the base is going to be log base A. I'm thinking of something else we could do first, just as kind of a separate step by itself before. It's not going to merge the logs together yet. It's just going to kind of handle part of the directions that they've written. Yep.
Raise 3 to the 4.
Right. We should put the 4 back as an exponent on the 3. And when we do that, what's 3 to the 4th power?
81.
Yep, 81. Okay, so now you've at least expressed factors as powers, but we still have to merge them into a single log, which we just mentioned the base was A. And when those two logs get combined together, they were addition. So what do we do with each argument? Yeah,
Multiply them.
multiply them. And 7 times 81? gives you 567. Okay, so that's combining two logs back together. Any questions on that one? All right, let's try another one. Let's do this one. This, though, let me just change this to 71. So we have 2/3 ln 8 minus the ln of 3 to the 4th minus 71. So they've left us a little arithmetic inside an argument for whatever reason. But let's start left to right, and we'll start doing things that we can do in that order. Anything that we could do first as we go left to right? Yep.
Raise 8 to the 2.
Right, raise 8 to the 2/3. And when you raise something to a fractional power, okay, the way I think of it is like this. 8 to the 2/3. That means square the 8, and then divided by 3 means to take what kind of root? Yeah, cube. Yep, take the cube root. You can do it in either order you want, but you have to take the number 8. You have to square it, and then you have to cube root it. And you do it in any order you want. So what do you get if you raise 8 to the 2/3? Yep.
4.
4. Yep. If you square it first, you get 64, and then the cube root is 4. Or if you cube root it first, you get 2, and 2 squared is also 4. So we get ln of 4 minus, what's 3 to the 4th minus 71? Yep. 10. And now our last step, when we merge those two ln's together, what's going to be my argument inside the parentheses? Yep. 4/10. And what is 4/10 reduced to? 2/5. Yep. There you go. So that's the natural log of 2/5. Any question on that one? All right, so I think that was the last one for 5.4, part 1. Okay, so part of the homework tonight will be the 29 to 33. All right, so we're going to finish up 5.4. Again, still looking at logs. And we're going to start by just looking at a problem and see if we remember properties of exponents and how we can use them to rewrite it. Okay, so I want to rewrite that. And when I'm done, I only want to have a to the x, a to the y, and a to the z. I don't want the exponent to have like a 2 next to the x or a 3 or a negative. I just want to have what you see right there. So we have arithmetic in the exponent. We have addition and we have subtraction. When would you add two things together in an exponent? What's the rule for when you do that? Yeah? Okay, something with the same base. We need a little bit more. Yeah?
When you multiply exponents with the same base.
Right, when you multiply expressions with the same base, you add the exponents. So forget about the minus c for a second. Could someone just tell me, how could I get that? Or what would this have come from to cause me to put a plus sign right there? What would that problem originally have been? Yep.
A to the 2x times
a to the 2x times a to the 3y. Yep. And because you're multiplying with the same base, you would add the exponents. Now we've got a minus z on the end. what would cause you to minus something in the exponent? Yeah?
Division.
Division. So what would we put here to cause the minus z? Yep.
Like divided by a to the z.
Yeah. Divide that whole thing by a to the z. Okay, so we've got part of what they want. It said write it in terms of a to the z. We've got a to the z now, but we still have a to the 2x and a to the 3y. I don't want those 2's and 3's next to the variable. Look at a to the 2x. What would that have come from? If you wanted to write something like a to the x, how would you end up multiplying that by 2 in the exponent? Yep.
A to the x squared.
Right, you would have had a to the x. So now you've written it in terms of a to the x squared. That would give you a to the 2x. And what about a to the 3y? How would that be written in terms of a to the y? Right, a to the y cubed. And the bottom, that's already just a to the z. Okay, so we took an expression that wasn't written in terms of a to the x, a to the y, and a to the z, and we now have an expression in terms of those three things. So just practicing our rules for exponents. Any questions on how we did that? Okay. So, we've done this exact problem earlier when we talked about exponentials. I think on Monday? Monday. We had a population of a town increasing at 2.5% every year. The population is starting at 50,000, and we figured out the amount of time for the population to double, okay, to reach 100,000. Well, we're going to solve the same problem again, but this time we're not going to graph it. Okay, we're going to solve it algebraically. So to solve it, first thing we have to do is remember our exponential growth formula and how we set all that up. Okay, so we're going to have an amount of people as a function of time. When you write an exponential growth formula, what's the first thing that comes after the equal sign? Not looking for a specific number, I'm just looking for what the number represents. Yeah?
The initial amount.
The initial amount. What was the initial population of this town? Yeah?
50,000.
50,000. Times. And what's the expression that goes inside the parentheses in an exponential growth formula? You don't have to fill in our specific value yet. I just want to know what in general is there, and then we'll fill something in. Nope, it's not going to be a 2 because the population is not doubling every year. What's inside those parentheses in general? Yep.
Like the percent increase.
Yeah. So what did we put inside there?
One-
Like the general formula for exponential growth. Just don't plug in anything from this problem yet.
1 plus r.
1 plus r. Yep. So 1 plus r is what should be inside those parentheses. But r, we have to make sure is a what? Yep, decimal. It's got to be a decimal. Okay. So what would we put inside the parentheses here if we now fill in the r value? What is 1 plus r in this case?
Wait, so one of ours,
I want to know what 1 plus r is.
the total population for 2 years.
So we're looking for a specific number that we're going to put in right there.
1.025.
Yep, perfect. 1.025. And then we have to raise that to the t. So that's the exponential growth formula. Now we have to plug in this 100,000. Where does the 100,000 get plugged in? We have two places we could plug it in right now. Tucker?
AFT.
It gets plugged in for A of t. Yep. So we've got 100,000 equals 50,000 times 1.025 to the t. Now, this is where we put the left in y1, the right in y2, and then we found an intercept. We're not going to do it that way this time. Anybody have a guess what my first step could be to start to get the t by itself? Yep.
50,000 both sides.
Yep. Divide each side by 50,000. And now this step we could have done before we knew logs. Right? Just divide each side by 50,000. And we get 2 equals 1.025 to the t. We've got a variable in the exponent. So what could we do with that equation to try to get it in a format we can get t by itself in? Yep.
Turn into a log.
Yep, change it into log form. That's exponential. Let's change it to log form. So if we try changing it into log form, what would my base be on my log? Yeah?
1.025.
1.025. All right, it's a little bit of an issue because I haven't talked to you about how to type in logs other than base 10 or e, but we're gonna talk about this. So there's my base. What's the logarithm going to equal? T. Logarithm always equals the exponent. And what's going to be the argument to my log? Yep, 2. So we have an answer for t. The problem is we don't know how to type that in. So we've got to figure out a way, at least this time, to get something equivalent to this that we do know how to type in. Okay? It's going to take another couple steps to figure that out, but once we figure out something we can type in, we'll compare it to what we don't know how to type in, and then that should teach us in the future how we can type this in directly, right into the calculator. So let's take this equation again. We're going to try to solve it, but we're going to do something a little bit different. Instead of rewriting it in log form by rearranging it, we're going to take the log of both sides. That's perfectly fine to do, as long as you do it on both sides. It's like taking the square root of both sides. Okay, so let's take the log of the left and take the log of what's on the right. So this is a different approach to solve for t. It's going to take a couple extra steps, but we're going to get something that's equivalent to this, and then in the future, we'll be able to use this. All right, what could I do on the right-hand side? Something we talked about today. Yep.
Bring the t to the front.
Bring the t to the front. So we have log 2 equals t times the log of 1.025. Now, how could I get t by itself? Yeah?
Divide by log of 1.025.
Divide by log 1.025. So what we've just done is we've solved for t again. Now we have t equals log 2 divided by log 1.025. And when we took the log of both sides, what base did we assume? Because I didn't write it. Yeah? 10. And 10 is a log we have a button for. So now, t equals, we have one expression. And then we also have t equals, and we have a second expression. What does that mean about what's circled in expression 1 and expression 2? If they're both equal to t, that must mean what?
They both equal each other.
They both equal each other. So now you know how to type something in when the base isn't a 10 or an e. Log 1.02, base 1.025 of 2 can be rewritten as the log of the argument divided by the log of the base. That's how you type in something that's not base 10 or base e. You take the log of the argument and you divide by the log of the base. And actually, you could do it this way too. You don't have to use common log. You could use natural log. And it would come out exactly the same. So if you type in log 2 divided by log 1.025, and if you go back and look at the notes for this problem, it was 28.07 years that it was going to take. If you do it with the ln, you will get exactly the same thing. 28.07. Just don't mix them. If you want to use ln's, use ln in the top and the bottom. If you want to use log in the top and the bottom. So if I had to figure out something like log base 3 of 10, base 3 is not one that we have a button for. How would you rewrite that so you can type it in on the calculator? Yeah?
Log 10 over log 3.
Right. Common log of the argument divided by common log of the base. Or, what's another way you could rewrite that we could type that in on the calculator? Yep.
Natural log of 10 over natural log of 3.
Yep. Natural log of 10 over natural log of 3. Okay, what we've just kind of figured out, but haven't really formally written it down, is called the change of base formula. Okay, this is illustrating the change of base formula. It is how you type in a log that is not a base 10 or a base e. Now, some calculators might have a feature that allow you to directly modify the base, even if there isn't a button for it on the calculator. But with the change of base formula, you don't need anything fancy. If you have a calculator that doesn't allow you to change this base number, it doesn't matter. Every scientific calculator is going to have a log button. So you'll be able to always do it with just a basic scientific calculator. Okay. So any questions on how we solved this problem algebraically? So now, doing it the way we did on the right, this isn't really necessary anymore. Okay? We know if we get a base that's not a 10 or an e, we know how to work with it now. Type it in and get the answer. If you forget, you could always go back to the way I did it on the right, and you're going to get exactly the same thing. All right, so the last thing we're going to look at is on the calculator. And it has to do with finding an equation that models a set of data. So in Algebra 1, sometimes if you have like a scatter plot, you might draw in a line that looks like it kind of goes through the points as good as possible. Right? When you draw a scatter plot and you put in a line of fit, you try to make it so you have as many points above the line as you do below the line. And sometimes you even get a couple points right on the line. Well, there's a way that you can calculate what's called a line of best fit. So the line of best fit isn't a guess that you're doing by hand. Like that was just a guess when I do that. The line of best fit takes every single coordinate, analyzes them, and figures out what is the best possible slope and y-intercept to make the best line that you can going through the points. Okay? And there's a formula for doing it. This is not a statistics class, so we don't look into how to do that by hand. But we're going to do kind of the same thing, but on the calculator. And we're not going to look at necessarily a line. We're going to look at a curve that fits the data. Because if you tried to draw a line through these points, I mean, you might draw something like that. Right? You've got some points above, some points below, but it's not really a good fit. Okay? A line is not what models this data. What models this data is a curve. So we're going to look at how we can use the graphing calculator to figure out what's called a power model for a set of data. So what a power function is it's like a polynomial, but it's a single term. And it could be something like 3x to the 5th power, or 2x to the 9th power, something like that. What is a little bit different than a polynomial is sometimes you see numbers here that are decimals. In a polynomial, you're not allowed decimals in the exponent. In a power model, you are. Okay? You can have a decimal in the exponent. So it's a single term. You're going to have to find the a value, and you're going to have to find the m value. You're going to plug those in, and that's how you write your final answer. The y and the x, they stay right where they are. It's kind of like y equals mx plus b. When you write that, you got to find the m and you got to find the b, but you leave the y and the x where they are. Okay. So and this is going to be again called a power function or power model. Same thing. All right, so the first thing we have to do is decide, is a power model the right fit for our data? Okay? Because not every scatter plot has a curve that's good for a power model. So that might be the question I ask you. Here's some data. Is a power model a good model for it? If not, maybe we do a different model. We're not learning different models. In statistics, you would, but there's all kinds of models. There's linear, quadratic, cubic, quartic, natural log models, exponential models, power models, which is the one we're going to be doing, logistical models, getting into trig modeling. There's all different kinds of ways you can take a set of data and figure out, is there a pattern to it? Okay? We're going to focus on what's called a power regression. The power model. So first thing I would do is I would give you a set of data like this. Okay? And I'll say determine if a power model is appropriate, and then if it is, find the model. So I got to scroll back up so I can show you how you determine if a power model is appropriate. So the first thing you do is you've got your table. You're going to take the natural log of every number in the table. And then what you're going to do after you take the natural log of every number in the table is you're going to graph all those points in that new table you just made. And you're going to see if the points look like they're in a straight line. If it looks like the points are in a straight line, then we are going to use a power model. Okay, so let's leave some room to write some more steps, 4 more steps. But I'm going to scroll down, and we're going to do this first. Now, the nice thing is using the calculator, you don't have to take the natural log of every single number in the table by hand. If we put it into the calculator, it can do it for us. So let's start with that. So first thing we need to do is type everything in on the calculator. So we're going to press Stat. We're going to go to Edit. Let's see. And if you have numbers that are already typed in, when you press Stat and then go to Edit, you can just highlight the number, press Delete. Don't highlight the list and press Delete, because then we have to fix it and get the list back. That's annoying. Just highlight the numbers in the list so your screen is blank like that. So we press Stat, we went to Edit. Now we're going to put in all the x's. I do them first because when you hit Enter, it brings you down. So all the x's should be in L1. And we're going to put the y's in L2. If you don't put them in L1 and L2, it's OK. But then we have an extra step later on. So it's easier if you put the x's in L1, put the y's in L2. Now, again, you might be thinking, well, wait, you said something in step 1 about taking the natural log of every number in that table, ln x, ln y. I didn't do that. I just typed in the table the way it was. Okay? I'm going to do that in a minute. Okay, does everybody have those typed in? All right, so what I want to do now is create a new table. It's a temporary table, purely just to see if the power model is a good fit. Once I decide it's a good fit, I can throw away this temporary table. I'll never need it again. Okay? I'll need the original table. But let's make a new table. And the way we're going to take the natural log of all the x's is like this. Press ln. And then you're going to press second 1. What you're doing is telling the calculator to take the natural log of every number in L1. So second 1 is how you get to L1. Those are all the values that we need. That's the natural log of 1, 3, 5, and 8. We're going to graph these, so 1 decimal place accuracy is plenty, because by hand you're not going to be able to graph to the 100th. We've got 0, 1.1, 1.6, and if we scroll to the right, there's one more, 2.1. Okay. Now do the same thing for the y's. Take the natural log of every number in L2. So we get 1.6. You get the same number because 5 was used twice. 3.4. And we've got 4.3 and 5.1. So I took the natural log of every number in that list. Now, what I didn't tell you is there is a different way you can do it besides taking the natural log. I think it would be harder for most people because to do it, you need special graph paper. You need what's called logarithmic graph paper. If you had logarithmic graph paper, then we could avoid what we just did. Who's got logarithmic graph paper? I don't have it either. So it's graph paper where the spacing changes between the lines. Just kind of show you what it looks like. And then each time you get to a red line, it goes up by a power of 10. So like you've got 0, 1, 2, 3, 4, 5, 6, 7, I'm sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then that's 10. And that's 11, 12, 13, 14, 15, 16, 17, 18, 19, 100. And then, so it just, the spacing, it kind of changes. It's kind of weird spacing. So we generally don't use it a lot. And it's going to be easier to just take the natural log of every number in the table. Then we can use regular graph paper. All right, so let's graph those points. And we're trying to see if these points look like they're in a straight line. If they are, then we're done with this table. We can throw it away. And we're going to find a power model on the calculator. If they're not in a straight line, then we're going to say, based on the natural log table, points are not in a straight line. A power model is not an appropriate tool for this data set. And we'll stop. All right, so we've got 0, 1.6, 1.1, 3.4, 3.4. 1.6, we're at 4.3. It's 1, 2, 3, 4, somewhere around there. And then 2.1, 5.1. 2, 1, 2, 3, 4, 5. So just inside there. Okay, so what do you think? Does it look like those dots are in a straight line? Yeah. Okay, because they look like they're in a straight line, that shows you that a power model is a good tool to use. All right. Now we're done with this table. We can throw it away. We don't need it anymore. All right. So now I've got to show you how you take this data and continue on to find the power model. All right. So I'm just going to change these a little bit. So we are going to find two values, but I want to make sure I use the letters that the calculator is going to use so I don't confuse people. So step 2 is to press stat, calc, and then we're going to go to option, I think it's option A, at least on my calculator. Option A, which is power regression. Power regression. It's option A on mine. Okay, let's do that. So we went to stat, we go to calc, go to power regression. If you put your x's in L1 and you put your y's in L2, there's nothing you need to adjust. If you didn't, this is where I told you there'd be an extra step. So all we have to do, because we set everything up that way, is go to calculate. Okay, so go to calculate, hit enter, and it gives us some values. Notice it gave us a decimal for the exponent. That is not a polynomial. You cannot have decimals in the exponent. That's what makes the power model a little different. Okay? Variable decimal exponents are perfectly fine. So you're going to write your final answer in the form a times x to the b. Now, our book uses different letters. They use a times x to the m. A times x to the b is the same thing. They use a different letter. Okay, so let's take a look. You do want to round that appropriately. So if we round that off, what's the a value? I think our a value is 8. Yep. 5. I'm going to round the a value to 5. And what do you think we'd round the b value to as a fraction? Let's pretend like those first 5 numbers just kept repeating forever. You see the same number repeating 5 times, it's okay. We'll just assume that it would keep repeating. Yeah? Right, that's 1 2/3. Let's just call it 5/3. Okay, so final answer, y equals a times x to the b. Y equals 5 times x to the 5/3. That is the power model for this statement. 5x to the 5/3. Now what I want to do is graph it and see how good is it. Okay, to graph it, I need to make sure I can see all my points on the screen. What would be a good value for my x min for all the points in my original table? And I'd like to not have any point right on the edge of the screen. Yep.
0.
Yeah, I think 0 is good. What would be a good value for the x max?
10.
Yeah, 0 to 10 is fine. How about a good value for my y min? Well, Marin, what do you think?
4.
You could do 4. I'd probably just do 0, only because I mean, we're going to be going so big on the y-axis. Whether you do 0 or 4, it's not going to make much of a difference, but 4 might look kind of close to the edge. And what would be a good value for the y max? Yeah. Yeah, I'd probably do like 180. Now, what we're going to do is go to y equals. Actually, we'll do something different. Clear anything that's in there first, because we don't want to have anything there. Now let's press second y equals. And we're going to turn on the first scatter plot. So where it says plot 1, plot 2, plot 3, hit enter on plot 1. And instead of having it off, just turn it to on. Make sure it says it's going to get the x's from L1 and the y's from L2. If one of yours says something different, like it's going to get the y's from L3, well, that's going to be a problem unless you put your y's in L3. So let's put the L2. You don't have to change anything else. The color, the mark it uses, none of that's important. Just leave all the settings the way I have them there. When you hit graph, there are your 4 points from the original table. Now, let's put in our 5x to the 5/3, and let's see how good of a curve that we got through the points. So 5x raised to the 5/3. So what do you think? Is that a good model for this data? Yeah, it's very good. Right? It goes right through the points. In fact, if you look back at, I don't know if the calculator was telling us this or not, but sometimes there's a number that it gives you that tells you how good of a fit it is. Okay, this one's not doing it, but let me go like this for a second. Let me turn the diagnostic on, and let me do the stat calc option A again. You're going to see an extra piece of information now. So it's going to still show you the A and the B, but it's showing you this R squared and R value. What these two numbers are is it's calculating how good your equation is for those points. if this value, if R came out to 1, it would be perfect. Right? You can't, I mean, it's 0.9 repeating. You can't get a better fit for this data than 5x to the 5 thirds. It's almost perfect. Now, if you change 1 point, let's mess it up so that it's no longer in as nice of a curve. Okay, so now that 240, it's not going to line up with the other ones anymore. When I go to calculate a power model, it'll still do it, but it's not going to be able to find as good of a line this time. So what this R is called the correlation coefficient, and it's still good, but it's not as good, right? It's still really good, but definitely not as good as it was before, because I messed it up a little bit. And you can see that the A and the B values changed correspondingly. Okay, in this class, we don't have to worry about how good of a fit that the curve is. In statistics, that is something you would do. Right? You'd calculate what you think your equation is, and then you'd analyze your equation and say, how good is it really? Is it a good fit or not a good fit? All right. So any questions on finding a power model on the calculator? Yes?
So, like, I was looking at the first points for like the ln(x) and then the ln(y).
Yep.
How did you find the rest of the points on there, like the 1.1, 2.4?
So I just typed in ln and then I put in L1. So I told the calculator to take the natural log of every number in list 1. Yep. Essentially what it's doing is it's basically like typing in ln, putting in a number, and I think you could put in a bunch of numbers. You might have to put them in like braces, but it's just saying take the ln of a bunch of numbers at the same time. That's all it's doing. Let me just see if you put it in braces. Does that work? Yep, that works. So that's how you can take the natural log of a bunch of numbers at the same time, and that's exactly what the table did. Yep. Or you can type in each number one at a time. It's just going to take a lot longer. Okay, any other questions on those steps? Because that would be something on the test that I wouldn't help you with. Like if you say, if it says find a power model and you say, I don't remember the button, that's kind of what I'm going to, part of what I'm going to test you on tomorrow. See if you know how to do it. Okay. All right, so 5-5, that's going to be for next time. So the homework, not doing 5-5, but we are going to put the 29 to 33 with that. Okay, so the homework is on 293. It's 29 to 33, 35, 43, 46, and 48. Okay, I will put the test topics in the video, and then I will be after school today for extra help.